Hello everyone, this is Srijit and welcome to the subject MCAC35 Advanced Database Management Systems. Today we are continuing the topic Database System Architectures and we will discuss parallel systems and distributed systems architectures. Parallel database systems consist of multiple processes and multiple disks connected by a fast interconnection network. It improves processing and input-output speeds. In parallel processing, many operations are performed simultaneously, as opposed to serial processing in which the computational steps are performed sequentially. Let's see different types of parallel machines. A coarse-grained parallel machine consists of a small number of powerful processes, like a powerful single system workstation, where we have multiple powerful cores. Massively parallel or fine-grained parallel machine utilizes thousands of smaller processes. And there are two main measures of performance of a database systems. First one is throughput. It is the number of tasks that can be completed in a given time interval. And the second one is the response time, the amount of time it takes to complete a single task from the time it is submitted. A system that processes a large number of small transactions can improve throughput by processing many transactions in parallel. A system that processes large transactions can improve response time as well as throughput by performing subtasks of each transaction in parallel. Two important issues in studying parallelism are speed up and scale up. Running a given task in less time by increasing the degree of parallelism is called speed up, while handling larger tasks by increasing the degree of parallelism is called scale up. Let's see them in detail. In case of speed up, suppose a fixed size problem executing on a small system is given to a system which is n times larger, then the speed up can be measured as speed up is equal to the small system's elapsed time divided by the large system's elapsed time. The speed up is said to be linear if the equation equals to n. Then, in the case of scale up, increase the size of both the problem and the system. So n times larger system used to perform n times larger job. So it can be measured as scale up is equal to small system, small problem elapsed time divided by big system, big problem elapsed time. The scale up is linear if the equation equals 1. Let's see again in detail. Consider a database application running on a parallel system with a certain number of processes and disks. Now suppose that we increase the size of the system by increasing the number of processes, disks, and other components of the system. The goal is to process the task in time inversely proportional to the number of processes and disks allocated. Suppose that the execution time of a task on the larger machine is TL and that the execution time on the same task on the smaller machine is TS. The speed up due to the parallelism is defined as Ts divided by TL. The parallel system is said to demonstrate linear speed up if the speed up is scale up relates to the ability to process larger tasks in the same amount of time by providing more resources. Let Q be a task and let Qn be a task that is n times bigger than Q. Suppose that the execution time of task Q on a given machine ms is Ts and the execution time of a task Qn on a parallel machine ml, which is n times larger than ms, is TL. The scale up is then defined as Ts divided by TL. The parallel system ML is said to demonstrate linear scale up on a task Q if TL is equal to Ts. If TL is greater than Ts, the system is said to demonstrate sublinear scale up. There are two types of scale-up implementations: batch scale-up and transaction scale-up. Let's see batch scale-up. Batch scale-up are used where the size of the database increases and the tasks are large jobs. Here, jobs runtime depends on the size of the database. A single large job, typical of most decision support queries and scientific simulations, are of this type. Here, we use an n times larger computer on n times larger problem. Next is transaction scale-up. Are used when the rate at which transactions are submitted to the database increases and the size of the database increases proportionally to the transaction rate. Here, numerous small queries submitted by the independent users to a shared database, typical transaction processing and time sharing systems. N times as many users submitting a request, hence n times as many requests to an n times larger database on an n times larger computer. These are well suited to parallel execution. Next, let's see the factors that limit speed up and scale up. A number of factors work against efficient parallel operation and can diminish both speed up and scale up. Speed up and scale up are often sublinear due to startup cost. That is, cost of starting up multiple processes may dominate computation time if the degree of parallelism is high. Interference. Processes accessing shared resources, example system bus, disks, or logs, compete with each other, thus spending time waiting on other processes rather than performing useful work. Then it is Q. Increasing the degree of parallelism increases the variance in service times of parallelly executing tasks. Overall execution time determined by slowest of parallelly executing tasks. For example, if a task of size 100 is divided into 10 parts and the division is skewed, there may be some tasks of size less than 10 and some tasks of size more than 10. If even one task happens to be of size 20, the speed up obtained by running the task in parallel is only 5 instead of 10 as we would have hoped. Next, let's see the interconnection network architectures used in parallel systems. Parallel systems consist of a set of components that include processors, memory, disks that can communicate with each other via an interconnection network. The main interconnection architectures used in parallel systems are bus, mesh, and hypercube. Let's see them in detail. First one is bus. System components send data on and receive data from a single communication bus. It does not scale well with increasing parallelism. The second one is mesh. Here, components are arranged as nodes in a grid, and each component is connected to all adjacent components. The communication links grow with the growing number of components in mesh and so scales better, but may require 2 root n hops to send message to a node or root n with wraparound connections at edge of grid. Then we have hypercube. Here, the components are numbered in binary. Components are connected to one another if their binary representations differ in exactly 1 bit. Here n components are connected to log n other components and can reach each other via at most log n links, and it reduces communication delays. There are several architectural models for parallel machines. Among the most prominent ones are those in this figure. Shared memory, processors share a common memory. Shared disk, processors share a common disk. Shared nothing, where processors share neither a common memory nor a common disk. And hierarchical, which is a hybrid of above architectures. Let's see them in detail. First, the shared memory. Processors and disks have access to a common memory, typically via a bus or through an interconnection network. It is an extremely efficient communication between processors. Data in shared memory can be accessed by any processor without having to move it using software. Downsides. One of the downside is architecture is not scalable beyond 32 or 64 processors since the bus or the interconnection network becomes a bottleneck. These are widely used for low degrees of parallelism, 4 to 8 processors. Next, let's see shared disk. All processors can directly access all disks via an interconnection network, but the processors have private memories also. The memory bus is not a bottleneck in here, and the architecture provides a degree of fault tolerance. If a processor fails, the other processors can take over its tasks since the database is resident on disks that are accessible from all processors. For example, is the IBM Sysplex and DEC clusters. It's now part of Compact running RDB, Oracle RDB, for early commercial users. There are downsides. One of the downsides is bottleneck now occurs at interconnection to the disk subsystem. Shared disk system can scale to a somewhat larger number of processors, but communication between processors is slower. Next is shared nothing. Here, the node consists of a processor, memory, and one or more disks. Processors at one node communicate with the other processor at another node using an interconnection network. A node functions as a server for the data on the disk or disks the node owns. There are no shared memory or shared disk in this architecture. Examples are Teradata, Tandem, Oracle NQ. Data accessed from local disks and local memory access do not pass through interconnection network, thereby minimizing the interference of resource sharing. Share nothing multiprocessors can be scaled up to thousands of processors without interference. Main drawback of this system is the cost of communication and non-local disk access. Sending data involves software interaction at both ends. Next, let's see the hierarchical structure. The hierarchical structure combines the characteristics of shared memory, shared disk, and shared nothing architectures. Top level is a shared nothing architecture. Nodes connected by an interconnection network and do not share disk or memory with each other. Each node of the system could be a shared memory system with a few processors. Alternatively, each node could be a shared disk system, and each of the systems sharing a set of disks could be a shared memory system. It reduces the complexity of programming such systems by distributed virtual memory architectures, where logically there is a single shared memory, but physically there are multiple disjoint memory systems. The virtual memory mapping hardware coupled with the system software allows each processor to view the adjoint memories as a single virtual memory. It's also called non-uniform memory architecture or NUMA. Next, let's see the distributed systems architectures. In a distributed database system, the database is stored on several computers. The computers in a distributed system communicate with one another through various communication media such as high-speed private networks or the internet. They do not share main memory or disks. The computers in a distributed system may vary in size and function, ranging from workstations up to mainframe systems. The computers in a distributed system are referred to by a number of different names such as sites or nodes depending on the context in which they are mentioned. The main differences between shared nothing parallel database and distributed database are that distributed database are typically geographically separated, are separated administrated, and have a slower interconnection. Another major difference is that in a distributed data system, we differentiate between local and global transactions. A local transaction is one that accesses data only from sites where the transaction was initiated, while a global transaction, on the other hand, is one that either accesses data in a site different from the one at which the transaction was initiated or accesses data in several different sites. Now let's see different types of distributed databases. We have homogeneous distributed databases and heterogeneous distributed databases. In case of homogeneous distributed databases, we use same software or the database schema on all sites, and the data may be partitioned among all the sites. And the goal is to provide a view of a single database hiding details of distribution. That means the user sees it as a single database irrespective of the distribution in it. The user doesn't see that the data is distributed among multiple sites. The heterogeneous distributed database, it uses different softwares or schema on different sites. And this goal is to integrate existing databases to provide useful functionality. So the heterogeneous distributed databases are used where we want to combine the existing databases, where the databases may be, the systems may be of different types or different schema are implemented at different sites. So we can integrate them to provide useful functionalities. Then we have already seen the difference between local and global transactions. A local transaction accesses data in the single site at which the transaction was initiated, and a global transaction either accesses data in a site different from the one at which the transaction was initiated, or accesses data in several different sites. There are several reasons for building distributed database systems that include sharing of data, autonomy, and availability. In case of sharing of data, users at one site able to access the data residing at some other sites. And in case of autonomy, each site is able to retain a degree of control over data stored locally. There will be a global administrator that manages all the data in the entire system, and there will be local administrators. These local administrators govern, or they control the locally stored data. So there is a local autonomy. And higher system availability through redundancy. So data can be replicated at remote sites, and the system can function even if a site fails. Since the data is replicated at several sites, we can still access the data which is lost at one place. There are disadvantages as well. So all these things added complexity required to ensure proper coordination among the sites. And software development cost, it is more difficult to implement a distributed database system as it is more costly, and we have greater potential for bugs since the sites that constitute the distributed system operate in parallel. It is harder to ensure the correctness of algorithms, especially operations during failures of part of the system and recovery from failures. There is also an increased processing overhead. The exchange of messages and the additional computation required to achieve inter-site coordination are a form of overhead that does not arise in centralized systems. Let's see the implementation issues in the distributed databases. See, atomicity is needed even for transactions that update data at multiple sites. The two-phase commit protocol, 2PC, is used to ensure atomicity in distributed databases. The basic idea is that each site executes transaction until just before commit and leaves final decision to a coordinator. Each site must follow decision of a coordinator even if there is a failure while waiting for coordinator's decision. 2PC is not always appropriate. See, other transaction models based on persistent messaging and workflows are also used. Distributed concurrency control and deadlock detection are also required in this architecture. Data items may be replicated to improve data availability. So we will replicate it a lot to make sure that it is available. The more the number of replications are available, the more users can access it simultaneously. This concludes the system architectures. Thank you for listening to my class. Next day we will see parallel database systems.